Thank you. Oh, we're on.
Yeah, we're on. We're on. Good evening. Hi, everybody. As usual, I'm the same curator who you've seen in the last few years. David Dvorkin, senior curator here, Air and Space Museum, historian of astronomy. And today, we're taking our second leap into a deep, deep universe with Professor Garth Illingworth. And as you know, this is the warm-up that we start with, and it is really up to you to ask the pointed questions. I'll just throw them a few softies, and then it's up to you to ask him some serious questions. But there is that one rule that you all know, and that is you can't ask him about anything he's going to talk about tonight. Okay? Are you good?
And we get a chance to redefine that if the question is difficult.
That's right. Now, I know a little bit about your early home life in rural Western Australia.
Exactly, long time ago.
That's a ways away. And you had a reputation for conducting, as a child in primary school, numerous experiments. And just curious if any of them exploded, and what were they?
Well, you know, when you play with chemistry items, some things happen, and actually it's part of the goal as a child, is to put together those things that look good, make flames, and make a loud explosion. And in fact, one of the things, of course, was being interested in astronomy. I thought trying rockets would be a good thing to do. So building little rockets and adding the chemicals and burning holes in concrete, but the rocket never went anywhere.
Oh.
But it was effective.
And you had a lot of room to experiment in.
Yes, that's right. I needed that.
How rural was it? Were you living on a farm? Or?
No, it was about 100 miles south of the biggest city in Western Australia, Perth, and it was in the outskirts of a small country town. So we had a lot of area around that we could get out and play and ride bikes.
And what were your mother and father doing while you were blowing up the house?
Well, they were generally somewhere else. As a child, you made sure that they couldn't see what you were doing.
Yeah. Well, what kind of family did you grow up in?
My father was an engineer in a big factory, and he was the lead engineer in the factory. And so it was a management position as well as engineering.
And your mom?
She was, a stay-at-home mum, looked after us as children and so on, but she loved to sing. And so she was a very good singer. So she would be in local productions, musical productions. So.
Did you sing as a family?
No, not really. I mean, I think some of us liked to sing, but particularly my mother. The rest were a little more agnostic about that.
And one of the things he's also given us a hint about is that he loves desolate places. And I'm just curious if that has anything to do with where you grew up. Would you call that desolate?
Oh, it could get that way, yes.
Yeah. But what kind of desolate places have you visited?
Well, I would say, we really like the Four Corners area here. That is fabulous country down there. Yellowstone north up into Montana, up through the Rockies is just spectacular. But, even going to Africa is one of the things that my wife Wendy and I have really enjoyed doing. And we've spent quite a bit of time taking trips into the Serengeti and renting a four-wheel drive and camping out. Very interesting camping in Africa. There are large animals.
If any of you have any directed questions along those lines, I'm sure he'll give us some interesting answers. You've also been, and as we're going to learn when you're formally introduced, that you've been in many different places. Space Telescope Science Institute, Berkeley, you name it. But there was one move that you made because of your wife.
Yes.
And I'd be interested to know what that was all about, and also compliment you.
Right. Yeah, so Wendy, my wife, is an economist, and she's been working in electric power issues, but we were living in Tucson at that time, and Tucson doesn't have a lot of opportunities for economists. And so she was finding it a little challenging getting a good position, and we looked around and talked about it, and she said, well, let's get a bigger city. And so we thought, well, a DC area would be great for that. There's obviously lots of opportunities here. And so I looked around then for a position, and so I went off to Space Telescope, and Wendy went off for with a big consulting group in Washington. So that was a good move for her.
There's a question over here. Oh, okay. Question right here.
So I know that all the Hubble stuff, all the images are sort of open source. For people who know like scripting languages, is there anything that can be done with those images that maybe isn't being done with them through the Space Telescope Science Institute, that maybe an amateur could kind of play with, or is it all pretty much all taken care of?
Okay.
Okay, did you say stripping?
No?
Scripting.
Oh, scripting.
Yes.
Oh, I'm glad to hear that. Okay. Speak up. I'm hard of hearing. So the question is, what can you do with those incredible images that are coming back that are pretty much open source, public access? And are you asking what can you do for science, or what can you do for aesthetics, or?
Sort of image processing, is it all being taken care of by the Space Telescope Science Institute, or is there things that they are not?
Yeah, I can certainly respond to that. Yeah, so the images are public domain, and you can do whatever you like with them. And the Institute sets up and does a basic level of processing to produce a really good, spectacular image with the instrument artifacts removed. But from there on, sometimes for a media release, they will do special things with them, but most of the time not. Those images are just in the archive, and they're freely available for anybody. And I know folks in the artist community often get those and then change them or build structures or paintings around them. So yes, you're certainly free to do that, and it's great to do it. It's just wonderful scenes in there, sort of beyond imagination when you actually go into it.
The Space Telescope Science Institute also has a Hubble Heritage group that is composed of photo artists as well as astronomers or photo artists with astronomy background. And they also have a what's it called? Source. Oh, well, my brain is having a senior moment.
You mean for the MAST catalog, for example?
That's right.
The archive where you can get all these images, yes.
It's called, when they invite the public to do things as a group.
Ah, okay.
I keep on forgetting, but have a look. It's beautiful stuff.
I think we were all sad to learn about Stephen Hawking's passing this morning. And my question to you is, do you have or had you had any personal interactions with Stephen Hawking in your scientific career? And if not, were there any things that he worked on that were significant to what you're doing?
Yeah, so I actually never...
Do you want to repeat the question?
Oh, yeah, sure, sorry.
You go ahead.
Oh, okay. Yes, the question about Stephen Hawking had died today, and the impact he had on, whether I personally knew him and the impact he would have had on the areas I work in. And no, I hadn't actually met Stephen. I'd been to Cambridge many times, but I'd never really overlapped with him. And, but, the imaginative, he was a scientist with brilliant insights and sort of a deep sense of challenging questions and asking them and then trying to respond to it. And so he set a stage in cosmology that was sort of framed a lot of the things that I do, which is much more focused on a particular aspect of that. But his contributions were, unmatched in so many ways.
Up there? Yeah.
You don't need to name names, but could you talk about the most frustrating or difficult professor you ever studied under?
Oh, that's probably going to be in his talk.
Actually, I've been pretty lucky with professors. There are tough folks that you get to deal with, but often the best response when you meet somebody who is difficult is to be a little difficult back. You often gain some respect that way. And so I actually don't have bad memories of my professors and so on over the years, though I do remember one who threw a chalk, not a duster for a chalkboard at me because I didn't do the right thing, but that's okay. That was a Latin teacher, Latin. Really? Yes. I didn't answer quite right, so I got the chalk duster.
Yes. Speak up. What is your favorite animal?
Yes.
Thank you.
Yes, I think Wendy and I love to watch cheetah. Cheetah are beautiful animals, and when they move, they are sinuous, and when they move fast, they are incredible. And so, you know, we spend quite a bit of time looking for cheetah. They are rare and hard to find, but when we do, we spend a lot of time sitting there watching them as well. And actually, my screensaver on both our computers is a little family of cheetah with the young ones just a few weeks old. Beautiful.
Go ahead. What inspired you to become an astrophysicist?
Yeah, this is interesting. You know, I started reading popular astronomy books in primary school. I have no idea why I chose those things to read. I think kids, you get fixated on something and get to really enjoy it. And so I had popular books with beautiful pictures in them. And there was a British astronomer, Fred Hoyle, who wrote some of these books and also wrote popular books as well, novels. So sort of this combination. I was just fascinated by what I was seeing there. So that was a long time ago, but it stuck with me.
Yeah, Fred Hoyle was really quite a writer.
Yes.
Many people said his science was just as fictional as his, as his fiction.
No, he was imaginative and very capable scientist too, but yes.
Right there, yes.
I'd love to revisit your camping trips to places in Africa. So can you please share a frightening, adventurous, or funny story of a camping trip at one of the places you've been to there?
Yeah, so
Asking about the most frightening or wonderful? Okay.
Yes.
Of your experiences in Africa.
Walking in Africa is always interesting with animals around. One time we were in Botswana walking with a guide in a national park, and you're not allowed to carry guns in national parks. And so we came through some bushes, and there was a lion hunched down ready to leap on us. Just 3 of us. So we stopped. The important thing is you don't move quickly when there are very large animals that are looking aggressive. And she went, "What? Well, who are these things?" And the guy said to me, "Give me your pocket knife." And I said, like hell, I'm not, excuse the language, I'm not moving at this point. And what good is a pocket knife? And so we stood, and then she went, "Oh," and jumped back and then moved back through the bushes. And he said, "Oh, the pride is over there. I can see their tracks. Do you want to go look more closely?" And we said, "I think we'll go the other way."
To follow up an earlier question, anything about the dark sky? Did you have a dark sky where you grew up?
Yes, yes. And the country towns or the country areas in Western Australia, I mean, it's like, again, 4 corners, you get out there fabulously dark. So you could see the Milky Way, the nearby Magellanic Clouds. It was just spectacular skies. So, of course, that must have been something that you sort of found you could really relate to as a child as well.
How many of you have seen the Magellanic Clouds? Now, you can't see them from here.
No, that's right, that very southern hemisphere.
Yeah, one of my professors said, "Why did God put all the astronomers in the northern hemisphere and all the good stuff in the southern?" And he's answering this question.
Yes.
I think it was a question up there, yeah.
If you could spend time or live or travel anywhere outside of Earth, like anywhere in the universe, where would you go and why, or where would you stay?
Where would you travel if you could go anywhere in the universe? Is that okay?
You know, as you might see a little later, I would love to go back to very early times. So hop in our TARDIS or whatever, our time machine, and leap back there and have a real close look around. It's one thing to look with a telescope, but to actually see it would be spectacular.
I think there's some hands way up there in the back. Yes.
No, I didn't, unfortunately. So, you know, I'd been to Cambridge many times, but I never overlapped with Stephen at any of the sort of activities or conferences I was at. They were typically different from his area in those days. I've sort of changed and become more into that, but I haven't traveled to meet him since then.
I would add just briefly that he had a habit of showing up at the museum here unannounced.
Really?
And wanted simply to look around and tour. At least that's what his we would get a notice up in the third floor. My God, Stephen Hawking is in the hall, and I would run down like mad. And so I met him myself back in '75, and of course I tried to talk with him, but unfortunately his machine wasn't working. So, but being in the same vicinity with him was transfixing. Let's put it that way. Who did you admire?
Oh, young. I mean, certainly Fred Hoyle. There were Allan Sandage. I mean, there are so many of these prominent astronomers that really set the stage in the field. And so there are many greats there as well. You know, obviously, this is the John Bacall lecture, and I'm going to mention a little about John too. And John was a person that I found very inspiring and has done just great things for astronomy. And there are many, many people like that.
Right there. And then you, sir.
Who's coming up in astronomy? Who should we be looking for next?
Risky question.
Who's coming up in astronomy?
Yeah,
Who should
right.
we be looking for next? Ooh.
I might take the fifth on that one.
Astronomers in waiting.
Yeah, right. I think I could get into trouble.
The red hat. There was one, and then you.
If you're not going to be an astrophysicist, what else would you have been?
Sorry, your question again?
If you were to use a different career choice, what else would have interested you?
Yes, this is fascinating.
Can you repeat his question?
Yeah, sure. Sorry, the question was what different career choice might I have made? And I very nearly became a geologist. I had a superb geology teacher in high school who took us out on field trips, and I just loved that, finding fossils in the middle of nowhere. And I did some courses, and I thought, maybe I should become a geologist. And then I thought, nah, I've been interested in astronomy for so long, I'm sure I'll be disappointed. So I sort of went back to the old career track.
But it would take you to desolate places.
Yeah, true, that's true. But telescopes take us to pretty desolate places too.
That's right. Okay, there was one over here. Oh, right there, yeah.
Tell us anything about the Australian space program.
What about the Australian space program?
Yeah, space is a tough and expensive business. And Australia is a relatively small country, and Australia made its mark in radio astronomy and has focused a lot on that, and now is growing into optical astronomy, but really in ground-based area, ground-based telescopes. So the Australians are involved in space projects, but the resources are not there to do truly major projects. But I know a few people who are thinking of some imaginative, cheaper, smaller projects that are building those up. But it's hard to do that unless you're a very wealthy country or group of countries. I mean, the Europeans even come together as the EU to do their major space projects.
Yeah, Australia is certainly a major partner with other nations in some of the biggest radio installations in the world.
Yes.
And certainly the optical astronomy at Stromlo and Siding Spring is first class down there.
Mm-hmm.
And you're also involved, Australia is involved in the GMT,
Yes, that's
Giant
correct.
Magellan Telescope, which is Smithsonian's involved as well. I think there was another question farther back, yes.
What was your first job in high school, and what did you learn from it?
First job in high school, and what did you learn from it?
First job, I'm trying to remember. Wow, that's a long time
While
ago.
you're thinking, if
Yeah.
you have an empty seat next to you, raise your hand. Okay. There are a few people are looking. Okay, thank you. Okay, continue.
Yeah, oh yes, sure. So one of the things that was quite common amongst younger people in Western Australia was to go out and work with the agricultural industry during harvesting season, and to help the collection of grain, wheat and grain and so on. And so you would work as collecting, measuring the trucks as they came in, and noting down the weights and keeping track of the grain that was coming in. So I did that several years in a row, and then I actually went up and worked on a big iron ore mine in the very far north. That was spectacular. So drove up there across the desert and spent time working in the electricians and then out with the huge dump trucks. And a very interesting job, but long hours and very dirty. So I didn't want that for a career, that's for sure. But it was very instructive.
So you had quite a bit of experience, real
Yes.
work experience there.
Yep.
Yeah, and that's a very practical thing.
Yes.
Usually can lead to a better appreciation of working in teams,
Yes.
working in large, vertically organized, hierarchical teams. And would you say that helped you at the Space Telescope Science Institute?
No, I think it's
Places
helped
like
me
that?
all along. I was involved with big instrument projects when I was at the Kitt Peak National Observatory in Tucson and what became the National Optical Astronomy Observatory. And there we're always working with large facilities, complicated instruments, and yes, you have to work as a team. And obviously when it came to Hubble and being deputy director, then you're really into management of truly major projects. And as you'll see, I do a lot now with JWST, James Webb Space Telescope as well. And they don't come any bigger or more complex than that one.
Now that raises a question in my mind. They don't come any bigger. But if I learn anything about astronomers, when they're building the biggest telescope in the world, they're also thinking about what's next.
Exactly.
Now, are you going to talk about that, or do you have any wild hair ideas that you would like to share with us?
I actually haven't put a slide in about that because I was running out of time, I decided in the end. But the astronomy decadal, every 10 years astronomers get together and look to what they would like to have happen in the coming decades. In 2000, it was decided that James Webb Space Telescope, a big, cool infrared telescope in space, should be the highest priority. We are at that point now where we need to be thinking about what we will do in the 2030s. And so there are 4 studies underway, actually, for 4 different types of major new telescopes, even more capable in many ways and different, of course, from James Webb. So hopefully the next decadal survey will choose one of those to go forward. And it does, I'll show you, it does take a long time to do these projects.
Exactly. There was a question up there. Yes. What's your favorite star and or planet besides Earth? You're
Actually,
including Earth.
Yes, right. Well, definitely Earth. A lot of variety there, and we can access it. Unlike Mars, which is fun, but getting there is going to be tough. I would say that I actually don't have a favorite planet in the sense of your question, but I do have a favorite galaxy, and you'll see that in the talk, and if I remember, I'll point it out to you. It's a very distinctive one.
Question right here.
You talked about observing the sky when you were young. Did you have a telescope?
Did you have a telescope when you were young?
Yeah, it is an interesting question because people have said to me, oh, you must have had a telescope. And in fact, I didn't. And I think I bought one at some point and then thought, oh, no, this is boring. You can't see enough. So I put it aside and went back to the books because there was far more information there. And of course, you could see much further in those images in the books because they were taken with big telescopes. So strangely enough, it wasn't having a telescope that got me enthusiastic. It was really the pictures in the books that I saw. The popular colored images were just spectacular. And so these days, of course, we have Hubble Images, which were never around then, but equally you can be drawn in and think this is just amazing. The insights we get about the universe from imaging with Hubble and our other big telescopes.
Did you ever look at something in a book and then see it through a telescope and wonder why it was upside down?
I don't remember making that connection, but I'm sure it came up. Okay. Things didn't look quite right in telescopes.
Okay, right down here.
And someone told me that there's going to be a prototype installed in front of this museum or the American history. Is that correct or not? Of the James Webb Telescope, or is that not correct?
Yeah, that would be.
Yes, there is going to be, and this is in planning, and I don't know if it's official or not, but there is a hope that we will bring the full-scale model of the James Webb Space Telescope back to the mall. It will be in front of the National Museum of American History. And if it all works right, it'll be the spring of 2019. But this is not official. If you're a reporter, please don't say that. But there has been. I'm curious, how did you find out?
Actually, someone from the Smithsonian just told me like an
Okay. Well, someone
Another
knows.
source, yes. You have a leak internally.
Yeah, we dearly hope it'll work. It's been on the mall before, and it has been touring around, and it is full scale. And the first time I saw it, in fact, was in Prague at a meeting, and I had no idea what the darn thing was. Somebody said, well, it's a McDonald's restaurant, but Czechoslovakian style. It's huge.
Yes, it is huge.
Okay, I think we have time for one quick question right there, I think was one.
What do you think, in your estimation, the chances are in the next, say, 100 years of really determining what dark energy and dark matter?
This is really challenging.
Yeah, the question is,
Yes.
what is the chance within the next 100 years, I prefer you ask next 5 or 6 years, of what dark matter really is? And did you say dark energy as well? Yeah.
Yeah, my wife tells me as an economist, you never make predictions for periods that long. You're going to be way off. Tens of years. Dark matter, we have a chance of detecting it, but we keep doing a lot of experiments and we keep not finding anything and narrowing the parameter space, as it were, the options that it could be. So maybe we narrow it to the point that it really becomes one or other of a small number of things. Dark energy is going to be even more challenging, I think. Neither of these, I think, we're close to answering. So it's clearly two of the great unanswered questions about the universe. It's the nature of dark matter and dark energy.
Gives you something to look for the next rising name in astronomy.
Yes, right.
Back there, yes.
What if someone already knows what dark matter is? How can he publish it and keep his credit?
Well, the Astrophysical Journal and the Astronomical Journal are peer-reviewed. And anyone is more than welcome to find them on the web and submit a paper, and it will be peer-reviewed and will be judged. It does have to be cleared in the peer review process. And if you know what a peer review, maybe you could explain peer review, since I have my peers don't like my stuff.
You're not the only one. I think we all have those experiences. But it's like when you submit a proposal. A group of people will sit down and evaluate it and rank it, critique it, and decide whether or not it's worth carrying forward. It's exactly the same with professional papers. We write it up, we submit it to the journal, goes out to 1 or 2 anonymous referees who write their comments and send it back to the editor, and then they send it back to us and we go, ugh, what were they thinking? and we respond carefully and try again. So it's the evaluation, exactly as it says, by your peers, by your colleagues.
And the wonderful thing about modern science, and I think this is not characteristic of any one country or any one discipline, is that peer review is completely blind to institutional background or anything. If you have a great idea, you can present it. You just don't have any guarantee of it going anywhere, and that's because of peer review. And typically it's anywhere between 3 and 5 readers. I sometimes get more because they start arguing.
Yes.
Okay, one last question.
So the question was about Mars, was it? And whether I would like to move there? No way. It looks a pretty miserable place. It's desolate.
It's desolate.
Yeah, right,
yeah.
You're right. It is desolate, but there are limits.
And on that,
and
we'll,
it's a challenge to
we'll
do
thank
as well.
you very much for great questions. We're going to sit down now. They're going to convert the electronics to some other mode and tell us when we can start the formal part of the program. Thanks a lot.
Thank you.
Good evening, all. It's wonderful to see all of you here in the IMAX Theater. And also, I understand we have guests in the planetarium tonight. It's a terrific turnout. Thank you all for coming. We're very pleased. My name is Valerie Neal. I am chair of the Space History Department and a longtime colleague of Dr. Dvorkin's. And on behalf of our interim director, Chris Brown, and indeed all of our staff, I welcome you here to the 2018 John N. Bacall Lecture. This program is part of the John N. Bacall Fellowship that is sponsored by the Space Telescope Science Institute and NASA's Goddard Space Flight Center. It's part of that fellowship program that the person who has been selected for it, a leading astronomer, is invited to spend time there at the Science Institute in residence and to undertake efforts to communicate contemporary astronomy with national and international audiences. And part of this fellowship then is to give a lecture here at the Air and Space Museum. So it has been our honor for very many years to host the Bacall Lecture here. We're delighted tonight to have Professor Garth Illingworth with us as the 2018 Bacall Lecturer. He is Professor Emeritus at the University of California at Santa Cruz in the Department of Astronomy and Astrophysics. No surprise, that affiliation, given what you've just heard about him. He grew up in Western Australia, where he was an inveterate tinkerer in his parents' garage, and they evidently were tolerant of this. He built many science experiments, as he mentioned earlier, because his school fostered experimentation. And as he said earlier, he did early on consider geology as a career because he liked these desolate spaces, but he ended up pursuing physics and astrophysics, which opened up the whole universe of seemingly desolate spaces, punctuated by galaxies and clusters of galaxies and all other kind of phenomena. He graduated with honors in physics from the University of Western Australia and took his PhD in astrophysics at the Australian National University, doing his observations at Mount Stromlo and the Siding Springs observatories. From there, Dr. Illingworth took a postdoctoral year at the Kitt Peak National Observatory in Arizona, and then was a Miller Fellow at the University of California at Berkeley. Kitt Peak took him back in 1978 and held on to him until he was invited to be deputy director at the Space Telescope Science Institute in Baltimore in 1984. In a few years, though, he was lured back to California to accept a position at the Lick Observatory of the University of California, which is a partner with the Keck observatories in Hawaii. So you get the trend here. He has been associated with all the major observatories in our country at least, and I'm sure some abroad. Through the 1900s and into the 2000s, Dr. Illingworth has parlayed observations with the giant Keck telescopes in conjunction with the Hubble and the Spitzer space telescopes to find and then probe the most distant galaxies yet seen in the universe. His many papers on the distant and earliest galaxies, co-authored with teams of astronomers worldwide, are among the most highly cited papers in the field. He won the 2016 American Astronomical Society's Berkeley Prize for his pioneering work on the earliest galaxies, and the next year he delivered the plenary lecture at the AAS conference on that subject. This is prodigious scientific output for any individual, but in addition to all of that, he's been very active within the profession of astronomy and astrophysics. He has chaired committees and study groups, and he has especially chaired the congressionally chartered Astronomy and Astrophysics Committee for 4 years, a committee that does plot out the future for research. He's also one of the early activists seeking the optimum design for telescopes beyond Hubble, and especially what is now known as the James Webb Telescope. Through his teaching and his many public outreach activities, he has worked tirelessly to keep astronomy alive and flourishing for the foreseeable future. Will you join me, please, in welcoming Professor Garth Illingworth?
Thank you. Thank you very much, Valerie. Well, good evening, and thank you all very much for coming out tonight. I'm very honored to be selected this year to be the Bacall lecturer. John Bacall was an amazing person, an amazing astronomer, and very inspirational. And so I will say a little about John, but we will need to switch over to my first slide, I think. I don't think I can do that. It is? Ah, good. No, actually, it's interesting. We're well back in the slides. I got to go in the right direction here, I think. I don't know why it started. There we go. Here is the beginning. And so here is an image of Hubble up in the top corner there. Spitzer in the top, let me think, right. I got to get the orientation correct here. And then behind me, the James Webb. So the two telescopes at the top are going to be at the heart of what I talk about tonight, which is the very early universe, galaxies in the very early universe. But before I get into that, I want, as I mentioned, say a few words about John Bacall. John was an incredible astronomer. He was a very vibrant and lively human being. Here he is in his kitchen, obviously excited about something or other. Wasn't clear what it was to me. But John was somebody who recognized very early the importance of Hubble. And he and Lyman Spitzer spent a huge amount of time working to continue to have Hubble. This is before it was launched, to save it when it was canceled. Big missions always go through cancellation times and very difficult times. So John put in a great deal of effort and was an inspiration and set an example for scientists for later missions as well. I knew John when he was at visiting Space Telescope Science Institute, and particularly when we were doing the early work on the next generation space telescope, and I'll say a few words about that too. And both in the context of the workshop that we held and also his leadership of the Astronomy Decadal Survey. There have only been a handful of these. Every 10 years we do a decadal survey. John was one of those people asked to do the job, took on the job, and did a fabulous job at it. So let me just say a few words about the early days of the next generation space telescope, which became James Webb. So this was 1989. We held the first workshop. James Webb is scheduled for next year, so 30 years away. It takes a long time to do these projects, to get the background, to think about the science, the technology, to get folks involved and on board and supportive of doing a project like this. But there were three major activities that occurred around this time: a big workshop, technical studies, and also involving the astronomy community's decadal survey. So let me just go on and say a little about this. But one of the things that John did was participate in our very first workshop, and the comments that he made there we found very valuable in thinking about the path forward. As I said there, we would also like to thank John Bacall, who introduced the workshop by sharing some of his experiences with the Hubble project. His pertinent remarks about the dedication of those involved in the development of HST of Hubble emphasized the deep and widespread commitment needed to bring about its success at any big project. And John was also good at recognizing aspects that were going to be important for the success of a project. International collaboration and cooperation was one in particular. And he obviously resonated with a comment from an audience member about it being a historic moment when you start off a project like this. and with so many people involved. Over 100 people from industry, government, and the science community came out of this workshop. So one of the things that then occurred was, as part of that next year, the Decadal Survey was underway, and I mentioned John undertook to carry that survey forward. I was a panel chair on looking at space projects, one of the two committees doing that. We recommended going forward with a 6-meter cool telescope way above the Earth, and we even were game enough to come up with a cost estimate for it. So this was nearly 30 years ago. In fact, the Decadal Committee decided this was a little too ambitious. They had other things they wanted to do and didn't accept this or recommend it. But 10 years later, as our next slide or a little further down will show, this is what's happened. It actually became the recommended project. But there are always a lot of steps along the pathway to doing a big project like this. A committee was set up to look at the future. They recommended a 4-meter infrared telescope. Dan Golden, who was the administrator of NASA at that time, looked at this, looked at their report, and thought, maybe this is a little small. And I love this quote. So he was at the American Astronomical Society meeting, give a talk. And he said, I see Alan Dressler here. All he wants is a 4-meter optic that goes from 0.5 micron to 20 microns. And I said to him, why do you ask for such a modest thing? Why not go after 6 or 7 meters? And of course, those of us who had been involved in the early days when we were talking 8 and 10 meters said, yea, verily, we like that statement. And then Dan later came back and said, let's go for an 8-meter. Well, that was very visionary, and it was great to have, but the hard work was ahead. NASA, Ed Weiler, the administrator at that time in the science division, got on board with this and asked Goddard Space Flight Center, and John Mather too, who was here a month ago, Nobel Prize winner for his COBE work, to start working on this project. And then Ed did what was a very formal step in NASA, but a very important one for a project, the formulation authorization agreement, which set up the stage for going forward with the project. The Decadal Survey chose it and said, let's do an 8-meter NGST, and that sort of started the real work on that program. 20 years later, we're about to make that move to launch the telescope. So here it is, very different from our original concept, spectacular telescope. This is astonishingly complex piece of equipment. This is something that I think nobody else on this planet, there's no other country that could build a facility like this. And this is one of the most ambitious scientific projects ever undertaken. So it's wonderful to see this coming together and thinking about launch in the next year or so. In fact, scientists are already putting in proposals. Somebody asked about peer review. In early April, thousands of scientists will put in proposals to use this in its first year. And peer review will take the place there of selecting those projects. So let me move on and now really start talking about galaxies in the early times in the universe and what we see with Hubble and with Spitzer that set the stage for James Webb. Somebody asked a question about dark energy and dark matter. We live in a very strange universe. So everything that you see around you here is a tiny fraction of the matter in this universe. The mass energy is largely in dark energy and dark matter. And just a little icing on the cake, as it were, that is all the baryons, all the atoms. And so I like to think of it this way, where dark energy and dark matter are the 800-pound gorillas in the universe, and, well, the matter is just along there for the ride, at best. So when we're thinking about our telescopes, one of the things that is fascinating about astronomy is that we come to realize time travel. So the light that comes from the sun takes 8 minutes to reach us. So the sun we're seeing as it was 8 minutes ago. From Saturn in our solar system, it takes around an hour, depending on where in the orbit it is. If we want to go to the nearest star or look at the nearest star Proxima Centauri the light is coming from that. It's taken 4 years to reach us. So that star is, we're looking at it many years ago, effectively. The center of our galaxy, if we look down here on the right-hand side, here is a telescope on the ground with a laser shooting a laser beam to do some very sophisticated analysis with what's called adaptive optics on the galactic center. 26,000 years it's taken for the light to reach us from the galactic center. But as we go out, these times become even more dramatically large. The nearest galaxy, much like our own, Andromeda, big, beautiful spiral galaxy, 2 million years to reach us. Then if we want to go out and look at the clusters of galaxies that Valerie mentioned, wonderful, beautiful objects again, and I'll show some more of these later. They can be billions of years for the light to travel to reach us. So now we're starting to get serious about looking back in time. And in fact, if we take Hubble and Spitzer and look, and the galaxy we found a year and a half ago is at the very limit of those telescopes, the light has taken 13.3 billion years to reach us. We're seeing this galaxy as it was 400 million years after the Big Bang. And what's even more impressive is how telescopes like COBE, like WMAP, and like Planck have actually mapped out what are remnants from the early phases of the Big Bang, the universe as it was 400,000 years after the Big Bang, so looking back 13.7 billion years. So we are seeing way, way back in time and being able to map out things that are incredibly impressive. And I have a little video here which just gives you a sense of the moving through space and moving through images taken with close by in our own galaxy to very deep image that was taken with Hubble that went out to this most distant galaxy, the one that is looking back through 13.3 billion years of time. It will pop up here as a little red object, and it's red because that's the way we observe it with our telescopes. I showed it to be blue because that's the way it would look if we went back in our time machine, our TARDIS, to actually look at it. So here is a interesting little figure which I call the history of everything, because it basically is. We have the Big Bang on the right, and then the expanding universe takes us through this period where the radiation, the light in the universe escapes from all the matter around it and then spreads out across time. Now this is a very strange figure. 90% of the universe is on the left-hand side of the screen here. Right, left, whatever. Your left, yes, that's right. And so 10% is actually here. And the reason I do this, of course, is that I'm going to be talking about this particular part. So the dark ages are where there are no stars, nothing at all, just gas and remnant light expanding with the universe. The first stars pop up, and this we don't know for sure, but I'm going to show you something later that is an indication of this, about 200 million years after the Big Bang. 100 million years later, the first galaxies probably come into play. We don't know, but the models and what we understand about the galaxies start at that point. And then there's a period here where galaxies start to grow dramatically, and I'll show some of that as well. So we're going to be looking inside this cyan circle, basically, at what we're learning about galaxies at very early times. Now, the challenge is that if you take Hubble images, even the best of them, and you look at them, what you see are these very faint, fuzzy little blobs of light. Everything we know about galaxies in the universe comes from analyzing these images like this. And they look red here because that's the way they appear to us in the telescope. But if I actually put an image up, and then this is sort of colored in a schematic way, these are some of the biggest galaxies at these early times, about 800 million years after the Big Bang. And I've colored them blue to give a sense of what they would really like if we hopped in our TARDIS and went back. So they're not really red like a lot of the images tend to show. That's just the way they look in our telescope. So let me now show you a little bit more of what these objects are like. So here we have, over this side, I need to look in the right direction here, a galaxy much like our Milky Way. We think of it as an analog, because of course we can't see our Milky Way like this, we live in it. But if we look around, this is a galaxy we think looks like the Milky Way. 100,000 light years across, huge, beautiful spiral galaxy. Here we have these large blobby galaxies that are a few thousand light years in size. But in the middle, what we have is a tiny little object. These are most of the distant galaxies in the early universe, are tiny blue objects like that one that's represented there. And so very, very small. So one of the things that astronomers do is they're always talking about redshifts, this curious little description of the distance, of the velocity, of how fast they're moving away. Of course, the universe is expanding, and the further away you go, the more rapidly the universe expands. And what that does to the light that comes from distant objects is stretch it out and make it look redder. And this is just like a train. If it goes by with a constant whistle, you hear the lowering of pitch as it goes away from you, or a siren that's constant. Not one of the whoop whoop ones, but one of the constant noises. As they go away from you, you'll hear the lowering of the pitch. It's just the same with light. And so what we do here is that we look at the objects we're trying to understand. You can look in detail. Right up in the top here, I just showed something where a schematic of how the light is often spread out through instruments. This is hard work. You're limited to small numbers at a time, and it takes a long time to do that. But what we are lucky enough to have is that for more distant objects, the hydrogen in the universe absorbs the very blue light, the ultraviolet light in the galaxy. And so it takes a galaxy, which on the upper left, whatever it is up there, and the upper left, yes, you're right. So takes this light and then turns it into something that looks like this as that gets absorbed. And so this distance, this motion through the universe changes the wavelength and gives us a way to actually measure how quickly it's moving away, and that we can turn into a distance as well. So when we take images with telescopes, we take pictures in different filters. And so we have a blue image, we have a green image, a red image, infrared image. And so when we look at an object and take these individual pictures, we look at a nearby object, we get light in every filter, in blue, green, red, the whole works. If we look at something that's going away from us, a long way away, much of that blue light has been absorbed. And so nothing shows up in some of these filters in the blue, but then we get this sudden appearance of the galaxy in the redder ones. And if we take it further out as far as we can go, in Hubble, there are these two beautiful cameras, and in that one, all we see is the galaxy in sort of 1.5 filters. This is really setting the limit that we can do with Hubble, and the reason why we need James Webb, because James Webb can continue out beyond this into the infrared and go to even more distant and earlier times. So I have a little video here, I think, which will start up, and we'll show you this moving different galaxies at different times. And so right out to the very end. And I'll run that again just because I think it's sort of instructive to look at the images at the bottom and see how they change as we go to more and more distant galaxies. And something that's at redshift 6 is moving away from us at 96% of the speed of light. The universe is expanding extraordinarily rapidly when you look at very large distances. So how, of course, do we find these objects? Well, of course, Hubble and Spitzer, as I said early on. But we do it with these amazing instruments that are on the telescope. Spitzer was launched in 2003. It's a little telescope, 60 centimeters. It has done amazingly well. It's a remarkable facility. Hubble has great strides, and has done that because of the servicing missions. We put a new camera on in 2002. This is the advanced camera for surveys. Holland Ford was the principal investigator, and I was the deputy principal investigator on that. And we worked on that for 7 years to get that together, working obviously with aerospace contractors, with Goddard Space Flight Center, which was the lead agency for that. And then the astronauts took it up, and here you see Mike Massimino putting the box-like advanced camera into the telescope. It had a problem, and in 2009, when servicing mission occurred, folks had to go up and actually repair that camera in a way which was never expected to be needed on the ground. It was an extraordinary challenge. And so when I gave this talk yesterday, this is John Grunsfeld. John was there. And then we wandered into the Hubble control room, and he showed us some of the equipment he used to actually replace the electronic cards in the advanced camera. That was incredibly challenging activity. And so the astronauts saved the day for us with what they did on this and put a new camera on, the Wide Field Camera 3. Now, if we go and look now, this is a somewhat complicated chart, but it's very instructive. So it tells how we have done with our new instruments on Hubble over the years. In 1990, before Hubble flew, the best we could do on ground-based telescopes was to push out to about half the life of the age of the universe to look at distant objects and distant galaxies. Hubble flew, and that just changed the name of the game dramatically. The Hubble Deep Field that was put together in 1995, that enabled us to go out to about, 1.5 billion years here, to push out to 1.5 billion years of the Big Bang. We updated the camera in 2002 with the advanced camera and made another huge jump out to almost 700, 800 million years, 800 to 900 million years after the Big Bang. Another camera, and we're pushing out almost into the realm of the first galaxies. We didn't get there, and we're barely scratching the edge of it. JWST will get into that realm. It looks as though there's not much left for JWST to do, but trust me, it's extraordinarily hard working out there. And there's a lot going to be going on as we're trying to understand and look at the earliest galaxies. So the instruments make a huge difference. These capability-driven scientific advances are sort of central to what we do. So here is a sort of schematic of the realm, the environment in which Hubble has played. And this is important for astronomers. The ability to couple with other telescopes, other regions in wavelength space, other capabilities is immensely important for understanding the very complicated objects that we see. So Hubble, Spitzer, Chandra, the big Alma millimeter, submillimeter array in Chile, and the big ground-based telescopes together have worked to do an awful lot in terms of understanding. But I was struck when I was thinking about this and put together what I've called our greatest observatory. Somehow JWST seems a little greater than great. And so that's why I called it the greatest telescope. In that time frame, there's going to be a new ground-based telescope, LSST, a huge European telescope, WFIRST, and a new observatory, which currently has a few challenges in terms of the administration support for it. Hopefully Congress will continue its support and we will get that telescope. So the framework becomes even greater than just JWST alone. And so when we take these telescopes, the important thing is to have a sample of objects that you actually want to work with in detail to try and understand what is going on at these early times. With Hubble has been, as it was in that previous image, in the center of this because it set the stage. And the first deep survey was done in the mid-90s, the Hubble Deep Field North, and this showed us remarkably, as you push faint, you see further in the universe. There were people who were very skeptical about this, and when this was done, they were rather surprised that in fact it worked as well as it did. So at that point, it really set a change of mindset for astronomers, and they began to think about doing very large surveys. Now, very large is a relative statement. The moon is on here for a good reason. Everything we know about galaxies in the early times in the first billion years comes from these fields. The total coverage on the sky of these fields is about the size of the full moon. We don't sample a whole lot of the sky. Fortunately, it's enough to give us a lot of objects. The Hubble Ultra Deep Field is over here. This is the deepest image in the sky, and I'll show you in a moment. And these other areas have been done at various times over the last decade with both the advanced camera and the wide field camera and have really provided us large samples, as I'll show you. But we are not really sampling the whole sky when we're looking at these very early times. It's very challenging. So one of the things that has played a major role has been the Hubble Ultra Deep Field. The first part of that was taken in 2003. And over the last decade, there have been 19 different programs which have contributed images in there, and we put all this together, and in fact it's so much better than the original that we've called it the Extreme Deep Field. And so this actually is 23 days of on-target integration, long exposure for a camera on Hubble, especially on Hubble. That's a big investment. 800 orbits of time have gone into this remarkably deep field. This is the deepest image of the sky ever taken. But there's, whoops, did I jump over one? No, there it is. There we go. So one of the things then that we do with all these insights that we get from these deep fields is trying to set up and establish what happens with galaxies. Now I'm going to be concentrating on the very earliest times down here, around 13 billion years ago, about 800 million years after the Big Bang. But this figure shows what has happened over the life of the universe with galaxies as they've grown and changed. So we're here, over here, the Milky Way with these beautiful spiral galaxies. This is late in the time of the growth of galaxies. There's a period here where there's very dramatic growth. Extreme star formation in these objects. I showed you these blue objects before, very clumpy, lumpy, very unlike what we see now in the galaxy we live in. A period of time where we went up through a huge amount of star formation in the universe. Stars were forming very dramatically and very quickly in lots and lots of different galaxies. And galaxies look very different in terms, these are sort of consistently sort of blobby, small blue things. Then there's lots of different structures that started to occur. And so I've sort of tried to characterize what was going on, diversity, complexity, evolution, transition in that time frame when huge numbers of galaxies were forming and growing. And then as we come to late times, we see more stability and order in galaxies. And then we also get into doing archaeology in those as we look back through doing local archaeology and trying to understand how they came about. And we combine that with our ability to look directly through our time machines to understand what happened over the life of all galaxies. Ah, yes. So I'm going to show you a video here. It was meant to pause at that point. That was curious. So what is going to run here, I think, let me go forward. No, videos. Is a simulation of the universe that shows the build-up. In the lower, down here at the bottom, is the age from the Big Bang. So this is a 30 million light-year box in the universe, run through a computer. What you're seeing is dark matter growing in this time frame. The camera is, as it were, is designed to swirl, is moving around to look at this. And galaxies are growing in the biggest dark matter halos. Stars are forming in there. You can see the white and growing with time and becoming bigger and bigger over the, where are we now? 2.6 billion years we've reached. Very substantial galaxies are starting to form in there. And you start to see what look like explosions. Supernovae are occurring in these galaxies. And active galactic nuclei, as we call them, big black holes. Light is being, they're turning on there and pumping huge amounts of energy into the galaxy. So this is the first 4 billion years of the buildup of galaxies in the universe. It is an amazing computer simulation of that early time, and beautiful to watch and to see this grow and see what happened there. So let me also now put into context why we are also moving out into the infrared. Hubble is a telescope that covers regions that our eyes cover, largely a visible telescope. It goes to the infrared a little bit, goes down into the ultraviolet. But as I mentioned earlier, if we want to go to very early times, we've got to go further out into the infrared with our telescopes. And one of the reasons is that we get to look through things better. So here are the pillars of creation, this magnificent image from Hubble from, I think it must be over a decade ago when the first one of these was made. And this was a repeat with the new camera. And so just spectacular to look at. Invisible light. Now if we go then and look in the infrared, the image changes dramatically. Suddenly it's full of stars. There's a lot more that can be seen in this. And the reason is we're looking through the dust. In the infrared, the dust becomes progressively more transparent, and we can actually see the forming stars that are associated with these pillars of dust and gas. Now, so for distant galaxies, there's an even more stunning reason why we go to look in the infrared. So this is an image of the most distant galaxy, that big red blob you saw, that big blue blob, GNZ11, in the visible. So there's not much there. In fact, there is nothing. We cannot see anything in the visible. It's all absorbed, the light from that, by the hydrogen in the universe. So here it is when we go to the infrared. So here is our infrared image from Hubble, our Spitzer infrared image. So we must have that infrared capability if we're to explore the earliest times. And so now let me just remind you again of this history of everything and the region we're talking about. I'm going to talk more about the first galaxies and what we expect to see with James Webb based on what we are learning from Hubble and Spitzer. But I'll also say a few words about a very recent result from a ground-based radio observation about the first stars. Interesting and controversial result as well. And so we're looking at a period here which runs from about 12.5 billion years earlier to about 13.5 billion years, looking back from now, or turning it around about 300 million, 200 million years after the Big Bang to close to 1 billion years. And here are the redshifts down here for folks who like to look at redshifts. And so here is an experiment that has unearthed what could well be the first light or first indication of the first stars. It's a huge radio experiment. It's this little box here. You've seen radio telescopes, huge arrays of radio telescopes. This is nothing like that. This is a little box, and there are 2 of these in the desert. Actually, there's 3. They use 3 different ones. So this is at the Murchison Radio Observatory in Western Australia, actually only 300 miles or so north of our hometown. And why would the NSF fund a telescope project and put it in Australia? Well, the reason is there ain't nothing there. You look around here and it looks pretty desolate. And I can tell you it is really desolate. There is nobody. There are no FM radio stations. There are hardly any cell phones. In fact, they're banned here now. But there virtually were never any there anyway. There were sheep and there were kangaroos, but that's it. And they don't emit much radiation. So this is the ideal place to do sensitive radio observations. And so these folks, about 10 years ago, started to develop this, some support from the National Science Foundation, and put together this experiment. And they were very dedicated. They worked hard. There were lots of skeptical people around. So I'm going to show you an astronomer plot with all its complexity, because this could be a Nobel Prize winning plot or it could not be. This is the first results that indicate something about the first stars, but it is pretty controversial. So here is the microwave background. So this is the light spread out, as it were, in a spectrum, like I showed you before. And so the microwave background shows this signal at sort of a little less than FM radio frequencies. This sudden drop, flat bottom, and comes back up again. This corresponds to an absorption of the 21 centimeter radiation from hydrogen at a redshift of 20, about 180 million years after the Big Bang. This has been predicted for a long time. Folks have written this up in textbooks about expecting to see a signal like this from measuring the whole sky. So these folks did it. So what's the controversy about here? Of course, it's one experiment. Even though these people are very respected experimentalists and radio telescope builders and observers and data processors, this is so important that there's a lot of skepticism. And so one likes to have confirmation from other facilities, which probably will come about. But the reason there's a lot of skepticism is this. This is what theorists expected. Now, I have theorist colleagues who would stand up at seeing this and say, these guys have got it wrong. The theory has got to be right. The observations are wrong. So, of course, this happens at various times. They are correct. So I don't know what is going to be the ultimate outcome here. This is a huge difference. It's much deeper. It's sort of in the right place, but it stays flat longer before it comes up, and it sort of goes back to about the same level. So folks are having a lot of trouble trying to explain how this could be so different from what they expected. One of the theories involves the interaction of dark matter with the early gas in the universe. This is not something that folks think is likely to have happened based on what we understand from galaxies nearby and dark matter interacting with atoms or baryons. So there's a lot of speculation here, but you see this 2 weeks ago is when this came out. So this is a hot topic in the astronomy community at the moment. And you can see with a difference like this exactly why that would be a hot topic. So let me jump on from first stars and say now, and I'm going to concentrate for the rest of the talk on first galaxies. So this galaxy, seen 13.3 billion years ago, GNZ11 was a very romantic name here that we give these things, sets the stage for the first galaxies. Obviously, we're seeing a galaxy here that can be a first galaxy, but we already think that this is probably about 50 million years old, so it's not really a first galaxy. So, but it tells us the first galaxies must have been earlier than this. That's interesting. So we need then to sort of gain some insights as to when the first galaxies came about and whether we'll be able to see them with JWST, as we've been hoping all along. What is amazing about this is that these two telescopes, which are relatively small telescopes by our current ground-based standards, and certainly Spitzer, as I mentioned, is sort of this big, have been able to measure and move into the JWST regime. But JWST is going to be needed to take that next step out towards the first galaxies. So the question is, what do the early galaxies look like? And so I'm going to just spend a little bit of time on this just to show you very quickly an example. And this is my favorite galaxy coming up here. So when we look at clusters of galaxies, we're looking at another cosmic telescope. The gravity in those clusters actually magnifies and distorts the light from behind, but particularly magnifies. So you take Hubble, take one of our telescopes, and look at a cluster of galaxies like this. The objects behind are actually magnified, and we'd have another telescope. Now, there are some limitations to this telescope. It's a little tough to work with. So here are 6 of these beautiful clusters of galaxies. They're not very far away. These are, let me think, I look back probably a couple of billion years, as I showed you one before. So you have a nice image behind. So here, this long arc is a distorted image of a galaxy behind. These are not very good optically, but they do magnify really nicely. And so let me show you an example of this. So back in '96, we were taking an image of one of these clusters, working on the big white-looking blobs here, the big galaxies in it. We noticed this very strange orange structure. We subtracted off this galaxy, and here it is. And we looked at this and thought, this is very weird. The color is strange. This looks like this, but just different magnification. Turns out the critical line in the cluster, the region of very high magnification, runs right through here. So these are 2 images of the same object. In fact, there's a third one over here. This cluster produces 3 images of the same object, each of them looking different. And so we can actually model what the gravity in this cluster does and remove these distortions, and here is what we get. So we get a 20 times magnified image of a distant galaxy 12.5 million years ago. So this is my favorite galaxy, and the reason will become apparent in a moment. So we took some images again, with the advanced camera, which improved it greatly. We see more structure in it. If you look over here, this little blob is, if we took the cluster away and looked, that would be all we could see. The cluster does an incredible job of changing this image. And so what we have then done is asked, can we find others? Well, it turns out we've looked for 15 years and we have not found another one. We've looked at over 100 clusters and this is still the best one. And so, did that not change? There we go. So this is the European ELT, the 40-meter, 39-meter telescope the Europeans are building. Since we can't find clusters to do this magnification, the only way we can do this is to take a very large telescope and use lasers and adaptive optics, which remove all the distortion in the atmosphere, and get an image of galaxies directly. And it has to be really big because it has to magnify a great deal to actually see these galaxies. So with a telescope like this, with the lasers, the adaptive optics, we'll be able to see many more of these objects. But for now, we just have that one example. But that tells us a lot about what these objects are probably like at early times. They're very complicated. They have lots of small regions that are forming stars in them, remarkably unlike our nearby galaxies like the Milky Way with all its structure. And so let me now just go on and talk about the very early galaxies and JWST's challenge in finding these. There's no doubt it will not be easy to find early galaxies regardless. They're very faint, and so it's been interesting to think about how we will do on this search for early galaxies. And there's an additional complication which we have realized recently for this, and that is that there's another graph of what we have been finding as we have looked at very distant and very early galaxies. And as we, no, I didn't put that in. My apologies. I missed one slide I wanted to add here, which showed an image of some of these most distant ones. But you've seen them before. They're very small, they're very blue, and they are very hard to find. We worked very hard with all the Hubble data, that picture of the moon with all the images there, and all we could find were 9 galaxies. But that in itself was enough to tell us that there's something strange going on again at early times. If we look at the numbers of galaxies, the density of galaxies on the sky, we expected, as you got out to this period about 480 million years, that in fact we would see numbers like this, and we don't. There's a big drop, and it's about a factor of 10 below what we expect. So this is interesting. Something is changing and happening at these early times. And so is this a problem for James Webb? This is an interesting question that we had. We would need to think about this. But we also wanted to confirm, is something really going on here, or are we missing something? Is something that we're not quite counting the galaxies right? Are things changing amongst galaxies at these very early times? And so there's another way to look at this. We can ask ourselves, we want to understand what this is going to mean for JWST, but also we want to see if this sort of change is something that we might have expected and might be confirmed by something else. And as in astronomy and science so often, you go off in a very different direction to answer questions like this. So this is a very different direction. Here are these 3 telescopes that measure the microwave background. COBE, way back, what was that? 1989, John Mather, who was here a month ago, got his Nobel Prize for the work he did on this. There was WMAP came next, and then recently the Planck telescope. Planck was an amazingly powerful telescope. It produced this remarkable image of the sky with all the structure in it. And what it also did when folks went out and did a very careful analysis of this structure was it told us something interesting about galaxies, which is rather remarkable. This light that we're seeing here is a reflection of conditions in the very earliest times near the Big Bang. 400,000 years after the Big Bang, all that structure comes from. But by careful analysis of the data, they realized that they were seeing that galaxies were only turning on really around redshift 10, around 480 million years. and providing a lot of light, ultraviolet light in the universe. This was a remarkable result, and this paper was something that played a significant role in trying to understand this period of early galaxy build-up. But for us thinking about the galaxies in early times, it was sort of a confirmation that very interesting things are happening around 400 to 500 million years after the Big Bang. And so we have this completely different path here telling us that galaxy production really turns on around this time frame. And then we have this change here also saying that something is going on at that time. And so, as I say here, it suggests dramatic changes in galaxies around redshift 10 to 12, around 350 to 500 million years. And this is interesting because JWST's first light goal is to try and understand what's happening in galaxies. And for some time, we were looking at theoretical expectations that a lot of that was probably going to happen at very early times. Such early times that it would be very hard for JWST to see any of that happening. JWST can push out to about redshift 15. What these two results together are telling us that there are big changes going on in galaxies, in the population of galaxies, the nature of galaxies around this time, just where JWST can see it. And so this I found particularly exciting as we're preparing to go forward with JWST now, saying, wow, we're really going to be able to get insights into how galaxies started and built up. So yes, my response to that, will JWST see the first galaxies? Probably, yes. I think quite optimistically that we will get to do that. And, but the reality will come home in a couple of years when the first observations really start to come in and we get to look at that. So in the title I mentioned cosmic sunrise. Astronomers have often characterized this period as cosmic dawn. And I've always found that somewhat of a misnomer since I see all these galaxies out there, and I always think of dawn as a very dark period before the light turns on. And if you're out in the desert and you see a sunrise, it just brightens dramatically and blam, the sun comes up. And it's incredibly bright. And I thought, you know, this is really what the universe is going to be like if we could go back and look as the first galaxies start to turn on. And so I like the analogy, the visualization, that galaxies are going to be bursting forth into the universe like cosmic sunrise around 300 million years or so after the Big Bang. And this is the way we will get to see this and get insights into this, is with this telescope. David was mentioning the model that he saw, and we may have it out on the wall here. This is interesting to see. When I think that we're going to fly this, it is huge. We're not going to fly that. But what we are flying as JWST is a huge project, a huge telescope. So there are people standing here under this. This is a very big facility to be flying into space. Very impressive. So let me just show you this little video here of James Webb recently, where it was transported down from Goddard Space Flight Center for some tests at Johnson Space Center in Houston. 3 months of tests in a vacuum chamber. And so putting it into a very carefully packaging up and sealing it inside a very large tank in a clean room and shipping it out through the doors, putting it at the end of a truck and taking it across town and getting to the Air Force Base and putting it into a C5. You can see this only just fits. Literally, it has inches of clearance. So we're building about the biggest telescope we can still transport around by plane. Truck goes with it, lands down in Houston, driven out in the middle of the night. You have to do all this in the middle of the night because you have to control a lot of traffic. How are we going? And so, okay. So I actually will have to jump over this because this took a little more time and continue out to the sort of final slides. JWST is going to be launched on an Ariane 5, and there's a nice video of this which you can see online. There is not time, unfortunately, to go through and show you this now. And so let me take... You want to show it? Okay, let me back up. Whoops. Let's see if it'll run now. No. Videos. Go. Yay, verily. So JWST is launched on Ariane 5. That's the upper stage. The spacecraft, the whole of the assembly moves out, and now we have to deploy it. And so the very first thing that you see there was the solar panel deploying. It's going to repeat just now because there's now a timer at the top showing the time from the start of activities. So in the first half an hour, this solar panel deploys and provides power. And it has to do that in that first few hours because their batteries do not have a long life. And down in the lower side here, it shows the spacecraft moving out relative to the Earth and to the Moon. So there's a huge sequence of deployments and orbital accelerations to get it pointed to the right place. It's going to go out beyond the Moon. As you can see here, it already is shot out there in 2.5 days. And now we are starting to deploy the sun shield. And so the two sides of the sun shield have come out. And so once they do, you'll see the covers starting to unfold eventually. So the structures are continuing to move out. There's a flap here, which is to balance the momentum on the spacecraft. And then covers coming out, coming off the sun shield on both sides. A lot of action here going on. Of course, it's over 5 days so far. So how many minutes of terror was the Martian one? 7 minutes. Okay, so we have a better opportunity to be terrorized. We're not going to get much sleep for a while. So now, one of the more tricky moments occurs where these booms pull out the sun shield. And the 5 layers of sun shield are pulled out. You can see this very fine capped-on material, coated. And then once they're fully out, they start to stretch apart. This is absolutely crucial that this all go well. This telescope is going to be cooled down by the space. This is going to shield from the sun all the radiation, the light from the sun. The bottom part is hot, but the upper part must stay cool. The secondary is now deployed and come out, the secondary mirror for the telescope. There's a radiator for the instruments that comes out here, so we're now up to 12 days. The wings of the mirror lock into place, and so now we have our full mirror. We have the secondary out. Optically, we have everything. Here is our telescope, 18 days or so out, and now we're moving out to the end of when it goes into the orbit 1 million miles away into a halo orbit in the Earth-Moon system or going around the sun. So this is a scary time, but an amazing goal activity here. So just quickly to finish up, there's an ensemble of things that we would love to do in the future that involve bigger missions in the future. We want to make sure that WFIRST happens because this combination of this very large telescope on the ground, JWST and WFIRST, would be immensely powerful for understanding galaxies as well as a lot of other things. In the 30s, we want to do one of these missions. These in themselves, UVOIR or another big telescope. There are 4 different ways of approaching different problems here. The astronomy community needs to make a choice and to make a recommendation. And so here, not the end, but the beginning. Thank you all very much. Sorry that ran on too.
Since I have tenure, I can say we can wait a few minutes and let's have a few questions. Are there any questions? But we can't go too long. And I also want to make sure that we entertain the planetarium people too. Yes?
In case something goes wrong with the launch deployment and can't fix, is there a consideration to build a second?
So what is if something goes wrong with the JWST, is there a consideration to?
Build a
or what are the contingency plans?
Yeah, so there are two things you could do, or three. You do nothing. You know, it's a huge project taking a long time. You don't do anything. Wow, that's not a good feeling. I mean, maybe four. One of them, of course, is everything works, and that's the highest likelihood. Everything works, and we get the telescope that we're planning. The project and folks at Northrop Grumman and at Goddard Space Flight Center are working like crazy to make this really work. Building another one is a real challenge. It would take a long time and a lot of money. I mean, you obviously have the capability there, but it's not something you do in even a few years. It would take a long time. The other one, of course, is servicing. Could you go out there and do something? Not in the time frame that we would have probably, as the telescope would cool off in ways it wasn't designed to do, and there would be problems doing that. So the crucial thing is that we make sure that this mission has a really high likelihood of success. And that's the approach that everybody is taking at this point. Mission success is the only criteria that we really must have in mind, having invested so much in this and being so important for the future of astronomy.
And if I understand it right, the JWST is undergoing full system testing.
Yes.
Which is something that the Hubble Space Telescope did not go through.
Yes, certainly the optical and instruments spent 3 months down at Johnson going through a full cold vacuum test. The fully deployed telescope cannot do that, unfortunately. It's just too big for any facility. But they're all being tested in two major separate components, sun shield and spacecraft, and then the optical telescope assembly and instruments. And then they'll be integrated, checked out, and then put all together and shipped off to be launched in Cruz.
One question here. How much further?
Yeah.
What's the?
Yeah, so the question was how much further away is JWST? A long way. So Hubble is only a couple hundred miles or something above Earth, very, very close. In fact, there's a little circle on that Earth picture up there showing Hubble. So, and JWST is way beyond the moon, about 1 million miles away. Very different situation. Much better for a big telescope, very stable. It can be kept very cold and uniform, unchanging. That's a great environment. Long way out, though.
Are there any questions in the planetarium? Nope. Okay, then in the blue right here. Any provisions for refueling the James Webb?
Yeah, interesting question. So James Webb's life is expected to be, is going to be limited by its station keeping capability, which is, you know, the propellant level in the tanks. And so we expect it to go at least 10 years, maybe a little longer, depending on how well that can be managed. There is always a possibility of going out there and doing something. We just don't have that capability at this stage, not like we had with Hubble, which was close by and was really set up to do that. This is, you know, at a stage in our development of a servicing capability that's sort of beyond what we can do or envisage doing, I think, in the next decade. But there actually is still the possibility that we could get out there if we could do it and refuel it, but unlikely, I would say.
Question right here.
No, unfortunately, we
Repeat
also.
the question, yeah.
Oh, sorry. Yes. So, could we still use it if it runs out of fuel? Unfortunately, not. It will drift away, and it will generally become unusable after that point. Some telescopes can continue to be used, but not this one. It's really dependent on having propellant available.
Yes.
No, there was.
Is there a launch date?
Yeah,
set?
sorry. There was a launch date. Not at this point. There was a delay announced last year. There's a very thorough effort going on to understand what the optimum launch date is, just to make sure that we go through. We have to launch this at a point where we fully understand that, you know, all the issues, bugs, everything has been worked out. So very thorough. We need to be careful about this. We spent a huge investment of time and money on this.
Yes, here. Yeah. Go ahead.
You talked about using it to look back at the very earliest galaxies. Are there other science proposals other than that that would be useful for?
Oh, of course.
Are there other things to you,
Yes.
that James Webb will look at other than the earliest galaxies?
Yes, I'm sorry. I should have mentioned this. Of course.
He's very focused on.
Yeah, I'm very focused, and you know, there was only 45 minutes, which I took an hour. Though I will admit I had a little problem there. So anyway, no. So it will do planets. It will do stars, nearby galaxies. We're looking at exoplanets. Should be a lot of fun with this. So everything that Hubble and Spitzer do, we'll do better with JW.
Okay, one there and then one there. Go ahead.
What type of propulsion is going to be on board the James Webb?
You know, I forget
What kind of propulsion? would
Yeah,
be,
what kind of
yeah.
propulsion? I forget what the particular propellants are. I should know. I heard it a few weeks ago, but I've just forgotten. But it's sort of the standard things that are used for maneuvering satellites. Sorry, there are people here who probably know that better than me. Yeah, thank you.
What was that?
Hydrazine.
What was that? Hydrazine and nitrogen I'll get it. Okay.
Yeah, thank you.
Right here.
That's good.
Currently, if we're able to look as far as the distance we can now and see things that existed relatively close to the Big Bang, do you ever think that in the future we could observe the Big Bang itself?
Can we observe the Big
Yeah.
Bang itself?
You know, it won't be with telescopes like this. It'll be telescopes like Planck that look at the cosmic microwave background. We won't be able to observe the Big Bang directly, but we'll be able to get more information at earlier times from doing better observations on the microwave background. There are plans afoot to do that. Again, very challenging experiments.
Right here.
30 years ago, when you first conceived of a next generation telescope, did you have any idea that this is what it would look like, or this is how large it would be?
No, we didn't. We had a sort of simple concept, but you know, the reality of doing studies and having the industrial partners come in with results changed the design very much. And so the basic parameters are the same. It's sort of 6 meters and so on, and passively cooled, but it looks very different.
Okay, we have 2 questions way in the back, and those will be the last ones. Yes.
So how deep will James Webb be able to look? Like 400 billion years or 200 billion years?
I think James Webb can push back to about 300 million years after the Big Bang. Maybe a little earlier, maybe a little later. It's sort of hard to know because it depends very much on what the galaxies look like then. But that's sort of the range. So back beyond is what we've seen now, but also in a lot more detail, a lot more objects. So we'll get a lot more information as well about even the things we see now.
Last question up there. Yeah, that's it. Go ahead.
One of the great things about Hubble is the spectacular photographs that we've gotten for the past couple of decades. What sort of PR photography would we expect from?
Good question. What sort of PR photography will be, imaging will be planned with the James Webb, based upon the fact that the Hubble was so transformative in its images?
Yeah, you know, the cameras that are going on James Webb are really state-of-the-art beyond what we've got on Hubble at the moment. I fully expect absolutely dramatic, beautiful images to come out, and we'll see lots of those.
Thank you very, very much.
Thank you.
And I want to once again thank the Goddard Space Flight Center, NASA, and the Space Telescope Science Institute for sponsoring the Bacall lecture. And I also remind you that the Exploring Space lectures are continuing. We have 3 more in April, May, and June, all devoted to aspects of the James Webb Telescope. And you can find their times and dates on our website.
Thank you. Good.
One final announcement. The observatory, unfortunately, is closed. We can't control the weather.